So in the previous videos, we have introduced the concept of thermodynamics. We have laid out some definitions. We have looked at how temperature and pressure are measured. We have looked at how they are defined. We have looked at what is a state, what are intensive properties, what are extensive properties, and we have looked at the state postulate. We have looked at processes, what are quasi-equilibrium processes. We have looked at what is a steady flow process, what are temperature, pressure, how are they defined, etc. We have also looked at the zeroth law of thermodynamics, right? Now it's time to take a more deeper dive and talk about energy in a little more detail than we have been talking about so far. And we're going to talk about energy, energy transfer, and energy analysis, right? So this is what the second chapter is about. So now, let's first do a sort of a thought experiment. So let us say that I have a room, right? So let's say it's a three-dimensional room, right? And I have a refrigerator in this room. So, and this room is sealed and insulated. Right. So, I have a room, I have a refrigerator inside the room, and that room is sealed, which means air cannot go into the room or come out of the room, right? And it's also insulated, which means no heat can escape the room, no heat can enter from outside, right? Now the question is, if I switch the refrigerator on and if I open it, if I open the front door, right? Now the question is, will I be able to cool the room down? That's the question. So what do you think? You don't think I'll be able to cool the room down. Why do you think so?
The exchange of heat was between the condenser inside, the evaporator inside the refrigerator and the condenser outside. So basically both of them are in the same room.
Yeah.
So there is no net heat transfer between.
So what you're saying is that the heat that I take out inside the refrigerator, I put it back into the room, right? And so there's no net change in temperature.
Yes.
Okay. Any other thought that comes? Same. Okay. You think same? Okay. What if I argue that the temperature of the room will actually increase? Why? Because we are supplying energy, right? So if, for example, I consider this entire room to be a system, right? And then if I talk about this as a system, then I know that that electricity which is powering the refrigerator is actually coming from outside. So there's energy transfer from outside to the system, right? Right? And is there any energy transfer from the system to the outside? There cannot be any heat transfer because it's insulated, right? And there cannot be any mass transfer or escape of air from inside to outside or vice versa, right? So there cannot be any energy exchange, right? So there cannot be any energy from the system to outside. So energy is being transferred to the system and no energy is being transferred from the system to outside. So which means what? What does that mean? So that means that the energy of this system must increase with time, right? And many times when you increase the energy of a system, you also increase its temperature. Many times, not always, but many times when you increase the temperature of when you increase the energy content of a system, you also increase its temperature, right? And so because this room has air in it, if I transfer energy to that air, it's most likely going to increase its temperature, right? So instead of cooling the room down, you would be actually heating the room up if you switched on a refrigerator inside a sealed and insulated room, because there is energy addition being done to the system, and so therefore the energy content of the system goes up because there is no energy going out of the system. So what is this that we have used to arrive at this conclusion? We have intuitively used something called energy conservation, right? Which means that we have sort of intuitively we have said that the total energy cannot change. It can only go from one place to the other. It can convert from one form to the other, but the total energy cannot change, right? And this is really a manifestation of the first law, but it is something that is very intuitive to us, that we have sort of inbuilt into us, right? But then if this is not really, if the total energy is not being changed, then why do we talk about energy conservation? Why do we talk about switching off lights and fans when we leave the room? Why do we talk about conserving petroleum resources? Why do we talk about energy conservation in general? Why do we talk about more efficient devices, more efficient power generation? Why do we talk about these things when the total energy seems to be constant? There is no energy wastage possible. So what does then energy conservation mean?
Not all forms of energy are useful,
Right.
so we need to convert them into usable energy.
Right. Right.
And
So what we are really talking about is quality of energy, right? When we are talking about energy conservation, we are talking about quality of energy. So what we want to conserve is certain types of energy because they are of higher quality compared to certain other types of energy. So for example, electricity is a very high quality energy, so we want to conserve that because it's very easy to convert electricity to something else like mechanical work or to thermal energy, right? But it's not always possible to convert all of the thermal energy back to electricity. We can convert only part or a portion of the thermal energy back to electricity, which is why we want to conserve electricity. Similarly, we have chemical energy in the form of petroleum like petrol, diesel, CNG, PNG, LPG, etc., right? So that's chemical energy, right? Because that's energy stored in chemical bonds, and we want to conserve that as well because that is also a high quality energy. We can convert that to thermal energy, but not always thermal energy back to petrol or diesel. That's not very easy to do, right? So we want to conserve that as well. So what we really say when we say energy conservation in a general sense is that we want to conserve the quality of energy. We know that the total energy does not change. What we want to conserve really is the quality, right? Okay. Now that being said, we need to look at more closely what this energy entails, what are the different forms of energy and so on. Okay. So let's look at energy in a little more detail. So broadly speaking, let's say I have a system of consisting of, let's say I have a water bottle. And it has water. Right? So I take 1 kg of water as my system. Now we know that this water has water molecules, right? And they are everywhere inside the water. And we also know that these molecules are moving around inside that water. So when something moves, they have kinetic energy, right? And so all these molecules, they possess a lot of energy, right? Plus there is interaction between the two water molecules, right? There are sometimes attractive forces, there are repulsive forces, there are forces that act between the water molecules. And when there are these kinds of forces, there is some kind of potential energy, right? So there is that. We also know that within a water molecule, so for example, we know that the water molecule looks like this. We know that, for example, the water molecule flaps like the wings of a bird, and that flapping has some energy associated with it. Although the OH bonds, they stretch as if they are springs, right? They stretch and compress, and so there is some energy associated with that as well, right? So there is this molecular type of energy where molecules either are moving about or are rotating or are flapping or bending or are stretching and contracting, right? There is energy associated with all of those. Plus we know that the hydrogen has a nucleus, and the nucleus has energy, right? Because if I do something to the nucleus, I know that there is enormous amount of energy that I can get, right? And I also know that if I take 1 or 2 electrons out of the oxygen, either I have to put in energy or I have to take out energy. So there is energy associated with electrons as well, right? So there is all kinds of energies even without us noticing that this energy is present. The air in this room, for example, has a similar kind of setup where air molecules are moving around inside the room even though we may not notice it, right? And those air molecules have energy because they are moving around, because they are vibrating, because they are stretching, because they are bending, rotating, and because they have nuclei and electrons and all of this, right? So there is a kind of energy that is because of its microscopic structure. Right? Because of the way the substances are made up. Now let's say I take this 1 kg water bottle and I lift it up by 1 meter or 2 meters, right? Then it has a change in potential energy. This has got nothing to do with the molecules rotating and translating and all of that continues to happen, but now it happens at an elevation, right? So I have increased its potential energy, isn't it? So I have another kind of energy which is called the macroscopic energy, and potential energy is part of that, right? And similarly, I take this water bottle, I throw it at 10 meters per second, I generate kinetic energy because I have now the water has kinetic energy that it did not have before. So I can measure that very well. It's m times v square by 2, right? So this is kinetic energy. So you can see broadly that there are 2 kinds of energies. One is a microscopic, the other is macroscopic. Microscopic is because of the molecular structure, molecular movements inside the system, and macroscopic is because the system is moving as a whole, right? As a center of mass it is moving, right? And so that has energy. And so this microscopic, the sum of all these microscopic energies is called the internal energy. U. And this is anyway called potential and kinetic energies. So, I can define a total energy E of the system, and the total energy is defined as a sum of this microscopic structural energy plus the macroscopic energy. So, I can define it as the microscopic energy U plus the kinetic energy plus the potential energy. And how is this defined? This is m times v square by 2. And this is, we know, is m times g times z, where z is the height from a particular reference point, right? So let's talk about potential energy, right? So what is the potential energy of this pen, which is 1 meter from the ground? What is it? Say m times g times z, right? But somebody could argue that I should measure the height not from this floor, but from the ground floor, right? And then I will have a different value of m times g times z, because z is now whatever 4 meters plus this 1 meter, right? So I will have a different value of potential energy. Which one is correct? Both are correct, or neither of them is correct. It should be from sea level. So if suppose somebody could argue that it has to be taken from sea level, and so arguing that Gandhinagar is about 80 meters above sea level, from sea level the height will be 80 plus 4 plus 1. So it will be 85 meters above sea level, right? So is that correct? Which one is correct?
It depends on the case.
It depends. No, I am asking you which
Actual
value of potential energy is the right potential energy for this object. Obviously, this object has a particular potential energy, right? And I must be able to say which one is correct, because different people will say different things, right? Which one is it? In practice, do we worry about it? What?
That depend upon the mass.
Yeah, of course it depends on the mass, but whatever is the mass, if I multiply it by g and z, I get a different number depending on what that z is, right? It may be 1 meter, somebody says it's 5 meters, somebody says, no, you got to take it from sea level, and so it's 85 meters. In all of these, let's say this pen is, let's say 0.1 kg. So 0.1 multiplied by 10 multiplied by 85 is 85. Sometimes it's 5, sometimes it's 1, okay? So if I take one person's argument, I get 1 joule. If I take another argument, I get 5 joules. Another argument, I get 85 joules, okay? So m is 0.1 times g is approximately 10 times z is sometimes 1, sometimes 5, sometimes 85. So total I get, sometimes I get 1, sometimes I get 5, sometimes I get 85 joule, right? I am getting different values of this potential energy. Now the question is, which one is correct? Or you can say the question is this even a problem? Right. So what you are saying is that the absolute value does not matter. What matters is what is the work that I got to do if I have to raise it by 1 more meter, or what is the energy that I am going to get if I allow it to drop by 1 meter, right? So this absolute value of energy has no meaning or very little use or meaning for us. What is of value to us, what is meaningful is what is the change in energy, right? So we can choose any reference point for gravity as we want. We can choose the ceiling if you want, and if you choose the ceiling of this floor, then you will get a negative value for potential energy, and that is absolutely fine. Why? Because the work done to raise it by 1 meter, or the work that it does when you drop by 1 meter, does not change irrespective of which reference point you choose, or in other words, it does not change based on the absolute value of the energy. So, the absolute value is not important. What is important is the change, right? Similarly, kinetic energy, right? I can take the Earth's reference frame, I can take any other inertial reference frame, I will get a different value of the velocity, and each time I will get a different kinetic energy. But what's important is, if I have to slow down some object from a velocity v to 0 velocity, what is the energy that I need, or what is the work that it will do for me? Or if I have to change the velocity of an object from v1 to v2, what is the energy that I will need to change the velocity, right? So, the change is what is important. So, similarly, the absolute value of the internal energy does not matter. What matters is the change in internal energy, right? And so, this is U plus Ke plus Pe. Usually, we talk about intensive property per unit mass. So, we talk about small e, the unit is joule per kg is equal to U plus small ke plus small p. So, this U is capital U by m, and this small ke is ke by m. So, this is m. So, this is v square by 2, and this pe is pe by m, which is equal to gz. Right. So, we can talk about the total energy of this system as comprising of its internal energy plus its kinetic energy plus its potential energy, or we can talk about, in intensive properties, I can talk about it as specific internal energy plus specific kinetic plus specific potential energy, where I have divided it now by its mass, which happens to be 1 kg in this case, but it could be 10 kgs or 5 kgs or whatever number of kgs, right. So, this then is the total energy of a system. The total energy E is U, which is internal microscopic energy, plus the macroscopic, which is the potential and the kinetic energies. So, if I add them 3 together, I get the total energy E, right. So, yeah.
Suppose the chemicals and petrols, the coal, all are the internal energy only, like it has?
Yes, this in the next video we will see what this internal energy comprises of, and chemical bond energy is certainly part of internal energy. So, chemical bond energy, nuclear energy, translational kinetic energy, rotational and vibrational kinetic energies, these are all part of internal energy.
Okay.
Okay, all right, we will end here, and in the next video we will talk a little more in detail about this internal energy.